Hi guys, welcome back to another past paper review video at Newton's Academy. Today we'll be looking at question 7. The question reads, study the reversible reaction represented by the balanced equation below. Initially, X moles of H2 gas is mixed with 0.3 moles of CO2 gas in a sealed 10 dm3 container. When equilibrium was reached, the concentration of carbon monoxide was 0.02 mole per dm3 and the equilibrium constant Kc at that specific temperature was 4. State Le Chatelier's principle. Okay, so for 7.1 it's just a simple definition question. Le Chatelier's principle is when the conditions of a system at equilibrium are disturbed, the system will react in a manner to reverse the effect of the change, okay, or of the disturbance. Okay, so in short, just to get a little bit of an understanding of what Le Chatelier's principle is basically just trying to reverse whatever happened to the system. So example, if the concentration of one thing was suddenly increased, the system is going to try and decrease that. If the temperature was suddenly increased, it's going to try and decrease that, and vice versa. So Le Chatelier's principle is basically type of a stabilizing principle. It likes to have it so that there's no major changes in either the reactant or product, and whatever disturbance does take place, we want it to be rectified as soon as possible. Okay, so that is Le Chatelier's principle. 7.2, state the initial number of moles X of H2 that was in the container. Okay, so in this case here, it's a really big question. It's 8 marks. And what we're going to use here for any type of question that's like this, for 8 marks, 10 marks, when they're asking you for the concentration, when they're asking you for the Kc value, whatever it may be, we're going to use the Rice table method. Okay, so I'm just going to put it here as Rice. Okay, so R stands for the ratio of the reactants and products. Okay, so just a rough table like that is okay. R stands for, of course, the ratio. The ratio is 1:1:1. Okay, that's the from the coefficients of the products and reactants there. I stands for initial. So the initial amounts of each of the products and reactants. So of course, for the products we have 0. So there was no products initially. For the concentration of for the number of moles of CO2, we have it as 0.3. And this here is, of course, going to be X, what we're trying to find out. Okay, then they're saying the concentration at equilibrium, the concentration of CO was 0.02. Okay, so CO is in our last column here, and at equilibrium it's 0.02. That means, okay, so E stands for the equilibrium and C stands for the change. Okay, the change from the initial to the equilibrium. So what we expect is to have a positive change on the product side and a negative change on the reactant side. So in this case here, you can see we went from 0 to 0.02. So we've increased it by 0.02. Okay, and what we can do is we can use the molar ratio to find out what is the change across all of them. Okay, so since the ratio is 1:1 for all of them, it's also going to be 0.02 here. So that's going to be 0.02. And here we're going to have minus. Why? Because it's on the reactant side now. So minus 0.02 minus 0.02. Okay, and for this one here, we're going to leave it in the form that it's in. So we're going to leave it as X minus 0.02. And for this one here, we're going to say 0.3 minus 0.02, and we get an answer of 0.28. Okay, from here, what we need to remember is that it is still in the mole form. Okay, so this last row here is going to be actually for our concentration. Okay, how do we calculate concentration? It's going to be C is equal to the number of moles divided by the volume. Okay, so we're going to start off here with our last column, and it's going to be 0.02 divided by 10 because the volume of the container is 10 dm3. Okay, and we get an answer of 0.002. Same goes for H2O. It becomes 0.002. Okay, for this one here we have 0.28 divided by 10, which gives us 0.028. And for this one here, I'm just going to leave it as is. Okay, so I'm going to say x divided by 10 minus 0.002. Okay, so I've divided the 0.02 by the 10, but I've left the x in that form. Okay, and this is going to help us later on when we are multiplying and trying to find out what the value of x is. Okay, the next thing to do from here would be to write out our Kc expression. So that's what we're going to do. So Kc is equal to CO, so the concentration of CO times the concentration of H2O all over H2, the concentration of H2 times the concentration of CO2. Okay, and from here we can just simply go and substitute what we have already. We know that the Kc is 4, which they've given us. So 4 is equal to the concentration of CO is 0.002. Concentration of H2O is the same. And the bottom of this is going to be H2, which we're trying to look for. So it's x divided by 10 minus 0.002. And the concentration of this here is going to be 0.028. Okay, from here we have all of our numerical values and we have the variable x. So using some mathematics and taking them over and dividing, we can get x to be equal to 0.3. Okay, and 0.03, sorry. Okay, and from there the question asked again, calculate the number of initial moles. So moles is N is equal to CV. So the concentration now is 0.03. So we can put it like that, 0.03, and the volume was 10. And we get an answer of 0.3 moles of H2. Okay, so that is our initial amount of hydrogen gas that was put into the container. The next question reads 7.3. The reaction is now carried out at a much higher temperature. It is found that the value of Kc decreases at this temperature. Is the forward reaction exothermic or endothermic? Explain your answer. Okay, so for this one here, quite a bit of theory is actually needed to answer this question. Okay, so what we need to understand is that when there's a temperature increase, according to Le Chatelier's principle, we want to decrease the temperature. Okay, so a higher temperature, we want to decrease it back to normal. How do we decrease the temperature? We favor a reaction that is endothermic. Okay, because an endothermic reaction basically states that when you have A and B, you're going to produce plus energy, of course. You're going to produce C plus D, for example. Okay, so we know that it's using energy, and therefore it will decrease the amount of energy available in the system. Okay, so when we increase the energy or increase the temperature of a system, according to Le Chatelier, we want to decrease the temperature. Okay, we decrease it by using it up. So we're going to use a reaction that uses energy, and in that case it's going to be an endothermic reaction. Okay, and they further went to go say that it is found that the value of Kc decreases at this temperature. And if the Kc decreases, we know that Kc, as stated here, it's the products. So it's the concentration of the products over the concentration of the reactants. So if the Kc decreases, so it's directly proportional to the products. So if Kc decreases, That means the concentration of the products decreased. And if the concentration of the products decrease, because they're directly proportional, if Kc decreases, the concentration of the product decreases. And the only way the concentration of the product will decrease is if the product is now being used to form the reactants. So the reverse reaction is taking place. Okay, so in this case here, the question again reads, the reaction is now carried out at a much higher temperature. It is found that the value of the Kc decreases. Is the forward reaction exothermic or endothermic? So let's just put together all that we have dissected from this question. We know that when temperature is high, we want to decrease temperature using a reaction that uses energy. And then in this case here, it's going to be the endothermic reaction. Okay, so it's endothermic. Thereafter, we've gone on to the second part of the Kc decreasing. If the Kc decreases, since Kc is directly proportional to products, the products were being converted to reactants. That means the reverse reaction was favored. So in this case here, it's going to be reverse. Okay, and finally, the question states, is the forward reaction exothermic or endothermic? So we know that the reverse reaction was favored and the reverse reaction is endothermic. Therefore, the forward reaction is going to be exothermic. Okay, I hope this makes sense.